Hello everyone and welcome to Hofstra University to Science Night Live. A big welcome to everybody in the audience here today on the campus of Hofstra University, and a big hello to everybody who's watching live online. Let's give ourselves a round of applause for everybody live and on into the future here. This will be on the Hofstra University website. You can come back and look at this at any time you want. The order of business today is we'll have our lecture, and then there'll be questions at the end. You can come up to the microphone to ask questions of our speaker. My name is Bob Brinkman, and I'm the Director of Sustainability Studies at Hofstra University in the Department of Geology, Environment, and Sustainability. And I'm also the Director of Sustainability Research at the National Center for Suburban Studies. And tonight's a very special night. It's our second Science Night Live lecture series that we're hosting here. There's information about our final one for the semester, which is coming up in April, that will be given by Javier Skirko from the Department of Biology. So I hope you come for that event. Tonight's lecture is by one of our top young scholars here at Hofstra University. Scott Lefurgy has a Bachelor of Science in Biochemistry and a Bachelor of Music from the University of Michigan, and a PhD in Biological Sciences from Columbia. He's also completed a postdoctorate at Albert Einstein College of Medicine. Now, Scott has been an assistant professor here at Hofstra University since 2011. And was the winner of the prestigious Gesson Prize for Outstanding Scholarly Publications here at Hofstra back in just last year. His research is on enzyme mechanisms and enzyme engineering. Now, I have to tell you, he also performs in New York City and Westchester as a choral artist and an operatic soloist. Now, he told us told me that he would not perform tonight. However, if you take one of his classes, I am sure that he will. His musical activities currently on our campus, at least, are focused on his biochemistry lecture courses, where he does sing solos to his students. Well, tonight, I'm really pleased to introduce you to Scott, who's going to be speaking on Superdrugs, or Superbugs and Superdrugs, the future of antibiotics. Please join me in welcoming Dr. Lefurgy.
Thank you, everybody. Thanks for coming out tonight. I want to begin tonight's talk with a quotation from Louis Pasteur. Louis Pasteur is a French chemist and microbiologist. He is credited as being the father of microbiology. He invented vaccines against anthrax and cholera, and he also developed what's known as the germ theory of disease, this idea that disease and decay don't come from inside of a person, but they come from outside. They're caused by microbes, bacteria, and viruses. And here's what he had to say on the subject of bacteria and viruses. Messieurs, ce sont les microbes qui auront le dernier mot. Gentlemen, it is the microbes who will have the last word. Pretty grim quotation to start this talk with. So the last word about what? Humans and microbes have been at war with each other for thousands of years. Sometimes the microbes get the upper hand. The plagues of the Middle Ages, for example, and the perennial pandemics that we see sweeping the world. However, since the middle of the last century, humans have gotten an advantage, and this advantage has been antibiotics. Antibiotics have changed the way that we live. Instead of getting a scrape or a wound and worrying that it's going to become infected, you're going to have an amputation, and you'll get gangrene. Now you simply put a bit of ointment on it and cover it, and it gets better within a few days. When you get a systemic infection, such as a UTI, that's my attitude toward UTI, or an STI, or strep throat, or bronchitis, you take a pill, and within a day or two, you feel better. Cesarean section delivery is made possible by antibiotics, so that the incision does not become infected. In fact, all manner of surgeries are now possible. Open heart surgery, surgeries to remove tumors, plastic surgery, all of these rely on antibiotics to prevent subsequent post-surgical infections. And another use of antibiotics that has really changed the way that we eat. I was surprised to learn this, but it turns out that 80% of the antibiotics used in this country are not given to humans, they're given to animals, and not to sick animals. Antibiotics are given to well animals, because it's been shown that by giving a low dose of antibiotics in animal feed, you can increase the rate of growth and the size to which animals will grow, and also allows you to grow them in ever-increasing density, thus decreasing the price of food, but causing a potentially unforeseen consequence, which is that when you give antibiotics under these conditions, at low doses, that it's possible for resistance to develop. So now, we promised you a talk on superbugs and superdrugs. So let's begin with the superbugs. What is a superbug? A superbug is a bacterium that has become resistant to most antibiotics, even some of our last line antibiotics. That is, those antibiotics that we have recently discovered and are reserved for only the most serious infections. The existence of superbugs and their continued spread threaten to move us into what's known as the post-antibiotic era. And this is not my language. This is what the Centers for Disease Control, the UK National Health Service, and the World Health Organization call the coming era, once antibiotics are no longer effective at treating infections. And what this era will consist of is a world in which all of the benefits that I showed on the last slide are now in question. Where now you might become afraid of getting an infected wound, where you won't be able to have that surgery because your doctor will say that it's too risky to perform because you might die from a subsequent infection. You know some of the superbugs already. MRSA, methicillin-resistant Staphylococcus aureus. And what you'll notice about the superbugs as they come online is that they have already begun to change the way in which we live. After MRSA became widespread, you began to see some changes around the buildings. Public buildings started to have these stations outside of them, grocery stores, hospitals. You've seen them. What are they? Hand sanitizer. That's right. Yeah, so hand sanitizer stations is one of the ways that we've changed our lives. You see it everywhere. I'd like to introduce to you one more name that you should be on the lookout for. And that's this one. Carbapenem-resistant Enterobacteriaceae. It's a mouthful, so we're going to call it CRE. Enterobacteriaceae are a group of bacteria that include things like E. coli, the bacteria that lives in your gut, and Klebsiella pneumoniae, which is a bacterium that infects your lungs and causes wound infections and UTIs and other kinds of nasty problems. Carbapenems are some of our last line antibiotics. So the fact that we have bacteria that cause common infections that are now resistant to our most treasured antibiotics, the last line ones, is really a major concern. I'd like to define terms for a moment and distinguish between antibiotics and antiseptics. And to do this, I'm going to be using, throughout this talk, a picture of a bacterium. So this oval here represents a bacterium. This is the membrane. It separates the inside from the outside. And inside of it, we've got this guy. Do you all know who this is? Okay, good. So Pac-Man, and Pac-Man represents an enzyme, right? He's the one who eats all those little dots in the game, right? So much like the Pac-Man in the game, the enzyme is a little machine inside of the cell that carries out some kind of chemical process, whether it's metabolizing food or building up the structures of the cell or regulating what happens at what time. And here we have an antibiotic, which is usually given in the form of a pill, sometimes an injection. And I'm going to represent that with this little chemical substructure, right? So this is going to represent the drug. And when a drug enters a cell, it works out its activity by associating very closely with this enzyme. So it basically sticks in the mouth of Pac-Man and prevents him from eating the dots. So now the enzyme is not able to carry out its function, and if that's an essential function to the cell needs that enzyme working to survive, then the cell is going to be, well, very unhappy at the least, but it's probably going to either have to stop growing, because if it continues to grow, then it will fall apart, or it's just simply going to die. All right, so that's what an antibiotic does and how it works. An antiseptic, on the other hand, is an example of that hand sanitizer we talked about a moment ago. And hand sanitizer contains an active ingredient called ethanol. That's just alcohol. And the way that it works is rather than interacting with the enzyme, it basically dissolves the bacterial membrane, so the bacteria just completely falls apart. And so by contrast, it's a little bit like just blowing the bacterium up. We have quite a large number of these antiseptic types of agents. Chief among them is soap. Simply washing your hands under warm water is a very effective way of getting rid of bacteria. And you have things like toothpaste and mouthwash and deodorant, and all these things contain these sorts of antiseptics to control the bacteria that are on our bodies. But the thing about these is that you can't take them internally. Right? You can't simply, when you have a strep throat, pour bleach down your throat, because your cells are also susceptible to some of these agents, and we don't want them inside the body. Outside is fine, but inside is another story. And I'm going to use another analogy as we begin to talk about antibiotics this evening, and that's of a lock and a key. So in the same way that keys fit into locks, and one key fits into one lock, and a different key wouldn't fit into this lock, drugs and enzymes interact in kind of the same way. There's a shape complementarity, that you have to have a drug that's the right shape for the enzyme in order for that interaction to work. Now, the trouble with enzymes is that unlike locks, it's possible for enzymes to change their shape. And when this happens, it's called a mutation. And a mutation looks something like this. So you go from the original shape to a new shape, and now just as the key doesn't fit into this lock, the drug doesn't fit into this enzyme. And as a result, it's completely ineffective. Then we'll talk a little bit about where these mutations come from as we go through this talk. But this is the idea that I'd like you to have as we go through it. So mutations cause resistance, right? They cause the drugs to become ineffective. And I'd like to give you a bacterial geography lesson, if you will, for a moment. So here is that membrane. This is the cell membrane, and it's kind of a flimsy barrier on its own, but it regulates what comes into the cell and what leaves the cell. In order for bacteria to survive, in addition to this membrane, they have to build a cell wall. And the cell wall is a rigid structure, and it allows the bacteria to keep its shape. Some bacteria have innovated, and they've got an additional barrier, a second membrane. And we distinguish between these two types of bacteria. This one we call gram-positive, and this one we call gram-negative. That's sort of the basic two different flavors of bacteria. And the gram-negative ones seem to be, we seem to be seeing a lot more resistance in those types these days. So we have an outer membrane and an inner membrane. All bacteria have a chromosome. This is where the genetic code is carried, it's DNA. And this is basically the blueprints for the cell. It's an instruction booklet that tells which proteins to make, which enzymes to produce, what structures are formed, and so on. So, as pertaining to drugs, we have one protein that is produced that is an outer membrane protein that acts as a channel, and it allows the drug to enter into the cell, or at least into the space between the membranes that we call the periplasm. And another protein that is important for tonight's discussion is a protein that builds the cell wall. So this is a version of Pac-Man that instead of breaking things down, builds things up. And the drug that we have here, for example, could bind to the cell wall building enzyme and prevent it from making the cell wall. And if the cell wall isn't made, now you just have two flimsy barriers. And now the cell is susceptible to being killed. Now, how would resistance change this picture? All right, so here we are back with our cell wall intact. Now, it's possible for there to be a change in the DNA sequence. Now, how do DNA sequences change? Well, every time the cell replicates, that is, divides in two, it has to make a second copy of its DNA for the new cell. And that copying process is not exactly perfect. There are some mistakes that are made at a very low rate, but sometimes a mistake is made in exactly the right place. Well, from the bacteria's point of view, from our point of view, in exactly the wrong place. Because what it does is it will change the shape of this protein, much like we talked about the key changing shape. And now, the drug no longer fits into that protein, and it bounces off the surface. All right, so this is one way that you can become resistant. Simply the drug doesn't get into the cell. If you have a mutation in that cell wall building enzyme, now the drug won't fit into that one either, and it bounces off. So you can be resistant that way. The cell wall continues to be built. And this is exactly the case for MRSA. Right? So in MRSA, the cell wall building enzyme has been altered. Another possibility is that you could acquire a new piece of DNA, a little piece of chromosome that we call a plasmid. And this plasmid contains a few instructions for proteins. We call these genes. So a few genes, and maybe one of them causes there to be an enzyme that can now not simply bind to this drug, but also break it down. Right? So this is sort of like the key going into the lock, and then the lock breaking the key, so that it can no longer fit. It can no longer come over and block this enzyme here. Right? So that's another possibility. And this is how the carbapenem-resistant Enterobacteriaceae, or CRE, works. They have plasmids that direct the production of a certain enzyme that will break drugs down. Finally, you could have the production of another enzyme that causes the drug to be kicked out, so that even if it gets inside, it never has a chance to attack the cell wall building enzyme, it just gets kicked back out. So with these four different possibilities, you might think that it's quite easy to develop resistance. But actually it takes a long time, because you have to get exactly the right red X in exactly the right place. It's a little like playing the Powerball. Anybody play the Powerball when it went up to 1.5 billion? Right? A few of you did, I did. It was a tremendous amount of fun to think about what we were going to buy. But it turns out that this is sort of, the odds on this are really poor for a single bacteria. But now imagine how many bacteria there are in the world. Think about how many bacteria there are on your own body. There are 1 billion human cells in a fully grown adult. How many bacterial cells are there? 10 times that amount. 10 billion bacteria covering every surface of your body inside and out. If you were to collect them all together in one place, they would form an organ that was about 2 or 3 pounds in weight. Right? And they're performing important functions for you in terms of digestion and so on. So now imagine that each one of them buys a Powerball ticket. So you can see that resistance could develop pretty much anywhere, but it only really becomes a problem under certain circumstances. So let's talk about how resistance develops. Here we have a group of bacteria, and now let's imagine that through some natural variation, that is this miscopying of the DNA as it goes through its regular processes, causes some bacteria to have these changes, right? So they just have either they gain some new ability, right? The ability to break down antibiotics. It's sort of neutral. It really doesn't make a difference. And most mutations don't make any difference. Changing the DNA doesn't change anything. It's kind of like taking the collected works of Shakespeare and copying them, and you miss one letter. You might still be able to understand what that particular word means, and it may not change the context. But in a different word, if you change one letter, it makes a big difference. So, and even this is not a big problem, because there's not very many of them. But now suppose you go through a process of selection. And in the selection, maybe it's that you provide an antibiotic, maybe at a very low level, such as an animal feed. And now, all of the regular bacteria that didn't mutate are destroyed, they die, and only this one that has the special mutation survives. But what that one can do now is it can amplify, because all of its brethren have died off. Now, there's nothing to prevent it from multiplying into 2, 4, 6, 8. 2, 4, 8, 16, 32, and so on, until it fills up the space. Now you have an antibiotic-resistant infection. So let me recap at this point. So our big idea is that we have a lock and key model for enzymes and drugs. There's a complementarity, and the drug only fits into the enzyme, like a lock into a key into a lock. Random mutations will change the lock so that the key no longer fits, and this is what we call resistance. Bacteria can also use plasmids, that's those small pieces of DNA, to share the lock design. So that if one bacterium figures out how to evade the key, it can take that DNA, put it onto a plasmid, and now share it not only with other kinds of DNA of other kinds of bacteria of the same species, but also across different species. And it's possible that you can get multiple of these plasmids in a single bacterium. This is what we call multi-drug resistance. And this is what we're really thinking about with superbugs, right? How does a bacterium become resistant to more than one thing? It doesn't have to acquire all those mutations over time itself. It can borrow from its neighbors. So what is the goal now is that we have to make more keys to fit these new locks. We have to come up with new drugs that are going to be adapted to these changes. But the trouble is it's not really obvious how to do this. Enzymes are really, really small. You can't exactly see what the changes are that you're going to have to design around. And so the process that we use to develop the new keys is called drug development. Now let's talk a little bit about how resistance spreads. So once you get the resistant bacteria, how does it get out? And I'd like to use the example of CRE. So CRE started in 1996. It was found in a patient in North Carolina. And by 2001, there were several cases found in New York City. Of course, when it gets into a city, higher population density, it's going to spread more rapidly. But from New York, the next place that this particular bacterium was found, this is Klebsiella pneumoniae carbapenemase. So this is the name of the enzyme that causes the resistance. This enzyme was found in a bacterium in Israel, and subsequently found in Sweden, the United Kingdom, and Colombia. A second type of CRE was found, caused by a different enzyme, starting in New Delhi. And from New Delhi, it spread to Sweden, UK, and the United States. And this was happening sort of around the same time. Now, take a look at this map. What does this map remind you of? Something that you may have seen before. Maybe in the back of a certain magazine. Anybody been on an airplane recently? Right? This looks just like those maps they put in the back of the airline magazine, right? Showing you what cities they go to. And in fact, business travel, right? The possibility of international travel on a regular basis by everyone is one way that these bugs can now spread not only in a local region, but around the world, and rapidly. So how bad is the problem? It's possible to do surveillance in order to see what the rates of antibiotic-resistant bacteria are. And here's an example of one such map. So here's E. coli resistant to third-generation cephalosporins. Now, third generation is sort of like 2 steps back from carbapenem. And what we can see, if you see the scale bar here, goes up to 100%. We're reaching very high levels in South Asia, and we're reaching sort of concerning levels in North America and Europe. There's a couple of other places around the world where you're starting to see quite high rates. Now, compared to cephalosporins, which have been in use for much longer than carbapenems, the problem with carbapenems is not quite to that point. See, the scale bar here has changed. Right? So we're seeing more still here in Asia, but we're starting to come up here in the States and Europe. So if you compare these two, you see that the problem is much worse for certain drugs than others. What I find most disturbing about this map is all the countries that are labeled in white. It doesn't mean that they don't have resistant bacteria. What it means is that the public health system has not been able to produce the data for us to be able to score them on this scale. So this, I think, is perhaps the most concerning thing about this map. Now, how has the problem progressed in time? For Klebsiella pneumoniae, we see that for cephalosporins, those third-generation cephalosporins, where the map is starting to get quite dark, the trend has been in a pretty steady upward direction from 2000 up until present day. And for carbapenems, the resistance is starting only in the past decade, but is beginning to catch up with these other drugs. For E. coli, now in the United States, aminopenicillins, these are penicillins which have been in use since the 1960s, we see already quite high rates of resistant infections showing up in hospitals. For other types of drugs, fluoroquinolones actually attack a different kind of enzyme, not the cell wall building enzyme, but these attack DNA replication. These rates have come up. Right? This is an example of this is ciprofloxacin. For these other drugs, you see that the rates are still lower, but you notice that all of them are going in an upward direction. And carbapenems, here at the very end, have just started to tick up. The news media has taken note of these changes, which are somewhat alarming. The rise of antibiotic resistance, New York Times, BBC, on the cusp of a post-antibiotic era. Superbugs are everywhere, according to Slate. Newsweek declares the drugs don't work. And if you read enough of these, you may begin to feel as though things are going in a very bad direction. So here's what our Centers for Disease Control, this is U.S. government, says if we are not careful, we will soon be in a post-antibiotic era, and for some patients and for some microbes, we are all already there. So there's cause to be concerned. So the UK government sponsored a study of what the problem with antimicrobial resistance is likely to be in the future. So here are causes of death in 2014 to various medical problems. Cancer is still by far the big winner. Resistant infections are significant worldwide, but still not as bad as some things, road traffic accidents, diabetes. But it's projected that by 2050, that this share of death by antimicrobial resistant infections is going to balloon to 10 million and even overtake cancer as an important cause of death. And these deaths are projected to be spread out across the world and primarily affect Asia and Africa, but still with significant numbers here in North America. So, what is the future that we are going to be facing? And are we doomed? I would say no, because we're still in a position where it's possible to make some changes that can stave off the coming apocalypse. And so, I predict that we will not have to live in a future like this, or a future where we're going to have to give up surgeries, or a future where we'll be consigned to quarantines once again, as we were in the earlier part of the last century. Because we can still do something about this. But in order to know what to do, I think we should understand where we've come from. So, the next section of my talk is called How Did We Get Here? Penicillin was the first antibiotic to be discovered. It was discovered in 1928 by Alexander Fleming, a Scottish scientist. And it was derived from this mold, which is called penicillium crustaceum. Fleming was studying bacteria, and he came upon penicillin by accident. So here he was growing a petri dish of bacteria, and what he'd done, a petri dish contains something called agar, right? And agar is basically like jello. Right? So if you know jello, it's kind of a jello that has nutrients that bacteria like to eat. I wouldn't eat it myself, but he spread his bacteria out over this plate, and then left the lid slightly ajar for it to dry, and then went away for 6 weeks on vacation. So the story goes. When he came back, apparently a mold spore had floated in through an open window and lit upon the plate, where it had developed into this large colony. Of course, this ruined the experiment. But Fleming, fortunately, didn't just throw the plate away. He noticed something very curious about it, which was that in the region right around the mold, for some distance, there were no bacteria growing, but they were growing in other places on the plate. Now, he'd spread the whole plate with bacteria. So he reasoned that there must have been something produced by the mold that was diffusing into the agar and causing the bacteria here to die. So he decided to test his idea. He took the mold and cultured it in liquid. Now, when you culture this kind of mold, it grows only on the top of the broth, and it excretes whatever chemicals into the broth itself. So he had this mold juice that contained whatever this agent was. And he took a second petri dish, and he cut a dish into it, right? Just sort of like a razor blade, cut out a piece of the agar. And he took some of the mold juice and mixed it with a new batch of agar and poured that into this dish, let it solidify, and then streaked out bacteria of different types across the plate. Let it grow up overnight, and what he found was that, at least for certain bacteria, whatever this mold juice contained prevented them from growing. Certain strains it didn't, but many of them it did. And so he published this work, and it was roundly criticized and forgotten for nearly a decade, for actually over a decade. But he called the active substance penicillin, which is still the name that we use for it. Now, the next stage in the story is when Florey and Chain, who were scientists working in Oxford, who were looking for some type of antibacterial agent, came upon Fleming's work. Now, they were working on this because World War II had already started in Europe in 1939, and they were looking for something to put on soldiers' bandages that would prevent infections, because they had seen the ravages of World War I and all the amputations and all the soldiers who died in the trenches because of infections. And they were looking at his work on lysozyme. Right? Lysozyme is an enzyme that is present in large amounts in chicken eggs. And this is why chicken eggs don't spoil, because the enzyme actually breaks down the cell walls. It acts like an antiseptic. And in addition to that, they came across his work on penicillin and said, well, we should try this. And they got the penicillin and they isolated it the same way that Fleming had. But what they discovered was it wasn't pure. It had all of these other types of chemicals in it that were present in the mold juice. And they said, well, maybe it'll work better if we purify it first and get rid of all of these things. So they used chemical means to purify the penicillin. And then they gave it to a mouse that had been infected with some type of bacteria. So it had an infection. And what they found was that this purified penicillin cured the mouse. They were very excited. And they said, well, let's make another batch of penicillin and see if it can cure a human being. They went to a hospital, they found a man who had been injured and had an infection, and they gave him a dose of penicillin. And they waited to see what would happen. And the man got better for a while. And then unfortunately, they hadn't made enough penicillin to do a full course of treatment because they had no idea how much would be needed. And the man died. So from that day on, Shane and Florey said, we're not going to treat another human patient until we get enough to be sure that we can see them through the entire course. They published their work in The Lancet in 1940 and 41. And this date is auspicious because at that point the work had to move to the United States because of the bombing of Britain. In the United States, New York City actually figures prominently in the history of penicillin. So Gladys Hobby was working at the College of Physicians and Surgeons of Columbia University in Manhattan at 181st Street, and was trying to purify enough penicillin for their first human trials. And since they were still growing it on the top of broth, surface area was the limiting reactor. They needed as much surface area as possible and went to such lengths as even using the area under the seats in the lecture theater at P&S, putting a 2-liter reaction flask under each one of these so they would have enough material to work with. And for the distillation, they needed, for the purification, they had to distill the organic solvents, which they didn't have enough room in the labs to do, so they used the fire escapes overlooking Fort Washington Avenue to do this. I'm sure that was not within code. But nevertheless, they were able to get enough penicillin for the trials, and because of this work, the chemical company, which was then a chemical company, Pfizer, became interested in the penicillin project. Of course, Pfizer is now, I think, if not one of the largest pharmaceutical giants in the world. So Pfizer, centered down in Brooklyn, provided what turned out to be an essential innovation to this procedure, which was the use of deep batch fermenters. So Pfizer was trying to produce citric acid using fermentation rather than isolating it from citrus fruit, because it turned out you could get a lot more from fermenting bacteria or yeast. And these deep batch fermenters now allowed the media to be stirred in such a way that you could grow the mold not only on the surface but throughout the culture. So by using this method, they were able to get 10 times the amount of penicillin that they got from the previous method. Another innovation came when the US government started to get involved. And an idea was that the original strain of penicillin produced a certain amount of penicillin. But it might be that there was some wild strain of penicillin that produced even more penicillin. Right? Perhaps because it had come into contact with bacteria, it had evolved to produce more on its own. And so a nationwide appeal went out to housewives and grocers to send in their moldy fruit to Peoria, Illinois, where the Northern Regional Research Laboratory was. And these mold strains were then cataloged and tested to see how much penicillin they made. And they hit upon one, this particular melon, which is number 1951. This is not the year it was discovered, this is the 1,951st sample that was tested. So you can see the scale of the operation. And this particular strain produced 10 times as much penicillin as the original one. So now with the fermentation and the new strain, you got 100 times as much penicillin per liter as previously. This, however, not to be outdone, the scientists at Stanford decided to take this strain and mutate it. Right? They subjected it to UV and X-ray irradiation. This causes changes in the DNA at random, and some of those random changes, just like the ones that cause resistance, caused the penicillin spore to produce even more penicillin, probably by changing one of the enzymes that blocks the production of penicillin. And so this strain, the new strain, actually had 10 times more than this one, and altogether, you got 1,000 times more penicillin per liter than the original paper. So, with this set of innovations, they were able to produce a tremendous amount of penicillin for the war effort, because after all this is directed at the soldiers first. Now, the United States Army was not very keen on injecting soldiers with this experimental drug. So initially, penicillin was infused into the bandages that were given to soldiers. And I put 14 hours here because 14 hours was the average amount of time it took to get a wounded soldier from the front to the hospital. And it was during this critical period where if the wound were infected, that something could take hold that would lead to gangrene. So the penicillin-infused bandages prevented many amputations. The first safety study, and I put that in quotations because, well, it was kind of an ad hoc study, was in curing STDs. There was a group of British soldiers serving in North Africa, and that company had been ravaged with STDs, and that happened on both sides of the war, actually. And so these soldiers were injected with penicillin as a means of trying to cure them, because soldiers that are taken out of battle for any reason, right, are not useful to the war effort. And what was found was that these soldiers were cured within a day and then could go back to fighting. And so after this, the use of penicillin became widespread within the army. And the production level increased to the point where 2.3 million doses of penicillin were ready for our soldiers on D-Day. Now, this begs the question, did the enemy know about penicillin? And we do have some evidence that the study in The Lancet, produced by Florian Chain, had made its way to the German scientists. And because of that, they made requests to the various repositories where strains of mold and bacteria and plants and so on were kept at universities, the Pasteur Institute in France, and so on. And even the Florian Chain themselves. Now, Florian Chain had been warned not to give samples to Switzerland, who was neutral, because they were thought to be funneled to the Germans through that country. But as the German army moved across Western Europe, the German scientists would make these requests to these various repositories. And thankfully, of course, the curators of those repositories knew better than to give out the mold strains to those scientists, right? When an occupied army comes in, they simply play dumb. Now, apparently they were able to culture some of their own penicillium strain. They didn't have the sort of organization that the Allied side had. And so they were only able to produce maybe 100,000 doses by the end of the war. The effort on the Allied side was much more organized, had no duplication of efforts because of the organization. And really the scale of the effort was second only to that of producing the atomic bomb. And so the Germans were not able to have the advantage on the battlefield that we had. And so penicillin is often called the wonder drug that won the war. It certainly provided an advantage to us in the ground war in Europe. For this wonder drug, Fleming, Florian Chain shared the Nobel Prize for Medicine in 1945. And after this, the development of penicillin began. At this point, the molecule of penicillin was not known. It was simply the substance produced by the mold that could be purified and administered. So the first work that was set about was to determine the penicillin chemical structure, and this was credited largely to the work of Dorothy Crowfoot Hodgkin, who won the Nobel Prize for this structure. The penicillin structure contains this very peculiar four-membered ring, and four-membered rings were thought to be so unstable as to be impossible to be made, and there was an alternative structure proposed. But what made the difference in this case was this new method called small molecule X-ray crystallography, where the penicillin was formed into a crystal, and then X-ray beams were shot at it to determine all the positions of the atoms. We'll talk a little bit more about crystallography later in this talk. But she was able to unequivocally show that the four-membered ring did in fact exist. After this, of course, producing penicillin using mold may not be the most convenient way to do it, and so a total synthesis was developed by John Sheehan at MIT. And he used a new reagent at the time called DCC, which is a peptide coupling reagent. And he used this, I won't go through the scheme, to create that four-membered bond. So this is the DCC here. So it was a critical step in the total synthesis. Total synthesis turns out to be a rather poor way of making penicillin. The mold really know how to do it very well. And the biosynthesis was worked out during the 80s. And it turns out that penicillin is a simple molecule made from these three amino acids that are brought together into the penicillin core structure by an enzyme. The purple portion is cut off, and this red molecule is added, and you get the penicillin structure. It turns out that it's possible to block the pathway at a particular step, and you can isolate this penicillin core molecule that's called 6-APA. So the penicillin core can be isolated, and then in a separate step, this red portion can be added to it to complete the molecule. So Sheehan's DCC molecule turned out to be quite useful because the bond that you're forming between these two is also a peptide bond. So if you can isolate the core molecule, you can use DCC plus any acid, right? This R stands for any chemical group that you should choose. And you can basically make any version of penicillin that you want, elaborating this with any chemical structure you can think of. And so this process is called semisynthesis because this portion is made using biology and this portion is made using chemistry. And using this method, various penicillin analogs, right? So we can think of these as different keys that are ground to fit variants on the lock. So we have penicillin and 6-APA. Methicillin, you'll recognize, of course, from MRSA. Came out in 1960. Ampicillin, cloxacillin, amoxicillin. Among these, this is really the only one that is still given as an antibiotic. And why? Well, because soon after the introduction of each of these drugs, a resistant enzyme appeared. Because, as will happen, natural variation in bacteria will occur, and resistance will arise. But this was thought to be kind of a solved problem. Well, if we have things that are resistant to this drug, we'll just put on a different R group. Well, our luck ran out at some point. So, the fact that we have to keep producing new antibiotics every couple of years was predicted by Fleming. In his Nobel Prize lecture, he says the following: "It is not difficult to make microbes resistant to penicillin in the laboratory by exposing them to concentrations not sufficient to kill them. And the same thing has occasionally happened in the body. Of course, we know that it has happened many times. The time may come when penicillin can be bought by anyone in the shops. Then there is the danger that the ignorant man may easily underdose himself and by exposing his microbes to non-lethal quantities of the drug, make them resistant." So Fleming predicted the predicament that we are now in. So how shall we respond to this? How can we not be ignorant people? So let me tell you about some of the work that I've been doing to reduce our ignorance. And as we go forward, I would like to draw this analogy of the key in the lock a little bit further. As we consider the way that penicillin interacts with its target, which is the cell wall building enzyme, it really acts more like a key stuck in the lock. That is to say that the key goes in, but it doesn't come back out. And here we have a more magnified version of the slide from before with the outer membrane and the inner membrane, and that channel and that cell wall building enzyme. The penicillin comes in, enters the periplasm, and now the key gets stuck in the lock. Right? These molecules are now stuck to one another, and they don't unstick. Resistance comes when a second enzyme is expressed either from a plasmid or sometimes from the bacterial chromosome itself that is able to take each of these keys and break them so that now they're unable to fit into this lock. And thus, this enzyme acts as protection for the cell wall building enzyme. And this enzyme is called a beta-lactamase. What we would really like is for one drug, this new drug, that can come in and it would stick into all of these locks and get stuck in them, right? So that the beta-lactamase would not be able to break this down and itself would be blocked by the drug. In order to understand how that happens, we need to take a little bit of time to look at the chemical mechanism. So here's the structure of this penicillin molecule, and here's the enzyme. What's happening on the surface of the enzyme is that there is a serine amino acid that is present here in the mouth of the enzyme that presents this OH group, or a hydroxyl group. And what happens is that this oxygen atom becomes attached to this carbon atom, breaking the bond here. This is called the beta-lactam bond, and this ring here is called the beta-lactam. So the beta-lactam bond is broken, and we form a new bond between the drug and the enzyme. This is called the covalent intermediate. Now, this is the chemistry that happens with the cell wall building enzyme, and this is how the key gets stuck in the lock. It's stuck in sort of more or less a permanent fashion. The beta-lactamase, the second enzyme, has an innovation in that it allows a water molecule to come in and break the new bond that has just been formed. And in so doing, it releases the broken key, that is the inactivated antibiotic, and is itself regenerated to go through the cycle multiple times. So this is how beta-lactamases break down the drugs and cause resistance. Now, in response to beta-lactamases and their continued evolution, we have developed a number of new keys, that is, new keys for the new locks that keep evolving. So we started with penicillin, and in addition to all the penicillins, we developed a second natural product. So as penicillin came from mold, cephalosporins come from bacteria. And you'll notice that the structure is the same. They contain this beta-lactam square ring here, but they have a few elaborations. They expand the number of atoms in this ring, for example. They have appendages on both sides. A second generation of cephalosporins came in the form of cephamycins. These are also natural products from bacteria. Right? So bacteria use these molecules as sort of chemical warfare against each other. They're competing for the same resources, and one will produce a drug that will try to kill the other. And we were able to isolate these molecules and use chemistry to elaborate them to make them suitable for human use. There were several different generations of cephalosporins. We have fourth generation cephalosporins that have ever increasing complexity in these side chains. And then we come to carbapenems. Carbapenem is so called because the ring that previously contained sulfur now contains a carbon atom. So there you get carbapenem. And each of these drugs is not one drug, but it's a family of drugs based on the same structure. There are also these monobactams where this second ring is dispensed with altogether. And resistance has now been found to all classes of these antibiotics. So what are we to do? How do we handle these locks and keys going forward into the future? Well, I have a couple of ideas. Is it possible to use X-ray vision to see inside the lock? Because if we could see inside the lock, maybe we know how to design a new key. How does the key turn or get stuck? So I'm going to extend the analogy. We'd like the drug to get stuck into the lock. That is, the key to get stuck in the lock, the drug to get stuck in the enzyme and not come out. If the drug, however, turns and comes back out, it gets bent. Right? And that's what we call resistance. So what we'd like to know is maybe how does the key turn in the lock so that it becomes bent or broken? Or how does it get stuck? Could we grind some new keys? Are there new designs that we might go after? And then how can we make some of these new keys last longer so that we don't have to keep inventing new antibiotics? So for this part of the story, I need to take you back to my childhood, right, which is in the 70s and 80s. And in the 70s and 80s, we had a sort of an important discovery, which was the second generation of cephalosporins. So these were the good old days of antibiotic discovery. Cephamycins were discovered in Streptomyces bacteria, and these new structures had an innovation compared to the old ones called a 7-alpha methoxy group. I'll talk about that in a second. These were developed by Merck in 1972, first went to market in 1978. And by 1984, they were the top-selling hospital drug. Because when in doubt, give them Suboxone. Because Suboxone worked against every infection. Gram-positive, gram-negative, aerobic, anaerobic. It killed everything. For a while. Now, what do we call Suboxone resistant? So pretty rapidly, by the 90s, we had enzymes that were resistant to Suboxone, meaning that they could break the key, they could hydrolyze the Suboxone. And here, what do I mean by resistance? Well, if we take a look and compare a couple of enzymes. So here's E. coli AMP-C. This is a particular beta-lactamase that has a good score of breaking down cephalothin. I give that a score of 10, and a poor score of turning over Suboxone. Right? So this enzyme makes E. coli resistant to cephalothin, not resistant to Suboxone. Another enzyme, FOX4, that's also found in E. coli, was discovered in 1996, has a decent score against cephalothin, makes the bacteria resistant, but has a very good score against Suboxone. Now, the interesting thing about this is that the molecules of cephalothin and Suboxone, if you look at the chemical structures, they're nearly identical, except for two regions. One is the 7-alpha methoxy group, which in cephalothin is just a hydrogen atom, and this group out here, which it turns out doesn't really matter. So how is it possible that this small chemical change, that is this change in the key, has such a big impact on the lock? This is something that I'd like to explore, and this is something I've been looking at in my research. So how do we begin to do this? Well, we begin by looking at the sequence of the protein. That is to say, proteins are made of amino acids that are arranged in a string, and we can, by comparing the order of the amino acids in a protein, we can learn something about the function of that protein. And particularly by comparing enzymes that cause resistance to those that don't. So I've lined up the sequences of several enzymes that cause resistance and those some that don't, sort of above and below this line. And by lining them up, what we notice is that certain regions of the protein are identical. And these are the regions that are required for the key to fit in the lock to begin with. And certain regions of the protein are different. So in this yellow box here, what we can see is that many of the proteins that are above the line and are resistant are missing some amino acids here. That is, through the process of mutation, they have lost little stretches of amino acid. And it seems that these losses correlate with the resistance. We can also look at individual positions and look for substitutions. And we notice that at certain positions, all of the amino acids are the same, but they're different from the amino acids of the susceptible bacteria. So these positions are things that we're interested in looking at and understanding. But merely looking at the sequence doesn't tell us what those amino acids are doing. That is, how are they interacting with the key to make the lock turn. And so we're going to need to do something a bit more invasive. And this is where I talk about X-ray vision. We can actually use X-rays to see inside a protein. But the process doesn't work quite like Superbugs. You have to first generate a crystal of a protein. Now, it may surprise you that you can form crystals of proteins. You can form crystals of sugar and salt. Many of you have probably done this at home. Right? If you've ever seen rock candy, that's what I'm talking about. Those are sugar crystals. Proteins, even though they're these large, complex, and unwieldy molecules, will also form crystals under certain conditions. One of those conditions is that the protein has to be highly pure. And it turns out to be quite easy to produce highly pure protein. And we do this routinely in our lab here at Hofstra. Then it requires some chemical guesswork. We don't know precisely what chemical conditions will cause a protein to crystallize, because every protein is different. So what we do is we try 500 different conditions at the same time. And one of those 500 conditions, it turns out, caused our protein to crystallize. Fortunately, we didn't have to set those up manually. We had the assistance of what's called a crystallization robot that is housed at Albert Einstein College of Medicine with our collaborators. So we did some chemical guesswork, and it took about 2 to 8 weeks for those crystals to grow. Right? But given these conditions, we were able to get crystals. And now how do we get the X-rays to look inside of them? Well, we take them out to a place like this. This is called a synchrotron. And this synchrotron is called the National Synchrotron Light Source 2. And we are very lucky that it is located here on Long Island, about 2 hours to the east in Brookhaven. And what this is a ring that's about half a mile around. And so if the ring is half a mile around, divide that by pi, the diameter here is about 2 3/4 football fields. Just to give you some idea of how large this building is. It's quite a large building. And what's on the inside of this is a ring of very quickly moving electrons. And as these electrons spin around this ring, they let off X-rays. And those X-rays come off at a tangent to this ring. And it's possible to take these very high-powered X-rays and shoot them at the crystal. So the setup looks something like this. You have your X-ray source. You put the sample here on this stick. And as the X-rays interact with the sample, what they're doing is the X-rays will see the electron cloud that's surrounding all of the atoms in the protein. And it will interact with them, and sometimes the X-rays will be bent and scattered. And those scattered X-rays can be detected on this detector. And it looks something like this. Right, so here's your sample in the middle that's blocking the light, and here's the stick that it's sitting on. But all of these black dots that form this pattern are the result of X-rays diffracting around electrons in the protein sample. And since it's a crystal, you get them reinforced, and they form this regular repeating pattern. And this pattern is unique to my protein. And so the experiment goes, you take one picture of it like this, you turn the crystal by 1 degree, and you shoot it again. You take the second picture, you turn it a degree, you shoot it again, and you keep going until you get a whole set of these pictures. And there's only one protein that can exactly produce this complete set of pictures. And we put these into a computer, and a couple of hours later, it spits out the data, which are these electron density maps. Now, this is the chicken wire structure that's shown here. And if your crystal is pure enough and the X-rays are powerful enough, you will get something where you can actually see the shapes where the protein itself will fit in. The computer will thread your protein sequence through here in the best way, and then you can turn it into a picture that looks something like this. This very familiar looking protein crystal structure with these corkscrews and these arrows that represent features of the structure that we can easily interpret. So we get a picture of what the lock looks like. And here I've shown a picture of our lock, and I've just highlighted certain of these chemical groups that are presented by the amino acids here in the mouth of the Pac-Man. Sometimes you're also able to get a picture of the lock with a key stuck into it. And here's what that picture looks like. We were able to get sulfoxamide bound into our protein FOX4. And by comparing these two pictures, one of the things that you notice is that the lock changes in response to the key. Sort of like when you stick a key into a lock and the pins begin to move. So this is the moving of the pins of the lock. And if we superimpose these two structures, you can see that there's a lot of motion over here in this part of the protein, and a little bit over here, but not very much here in the middle. And so these motions might be important to understanding how this lock and key interaction takes place. So the particular structures that we got led us to hypothesize about how this particular enzyme turns the key in the lock. That is, when beta-lactamases react with cephalosporins, we always see a couple of things in common. One is that there's a piece of the cephalosporin that breaks off, and that it appears that as it goes through the process of binding and turning, that there are two important bonds that have to rotate. So we have to have a rotation around this red bond and a rotation around this blue bond before the key can come back out of the lock. And so I'm going to go through just a little bit of the data that we collected and talk about our hypothesis. And in order to do that, I'm going to have to draw some structural analogies, because it turns out we don't have snapshots of all of the different steps along the way of turning the key in the lock. We just have the last one. But I think I'll be able to show you that we can compare a very similar enzyme. So FOX4 and MC, it turns out structurally, are quite similar to one another. They share a lot of the same structural features. And while MC is a susceptible enzyme, and there are many structures of this that have been solved by other researchers, and FOX4, which is a resistant enzyme, there's only our structure that is available. So we can use these as an analogy to be able to explain how the key turns. And we're also going to use a couple of different keys to illustrate this. So we have the sulfoxamide and cephalothin, which differ only at this one position, the 7-alpha-methoxy here. This is our structure is the only one that exists that is bound to sulfoxamide, that has bound to a resistant enzyme. And so we're going to use moxolactam as a stand-in. It also has the same methoxy group. It simply has a different side chain down here. So if you'll bear with me for this, I think you'll find this interesting. So when it starts, the cephalosporin binds in a conformation, and the first goal is to make the rotation around the red bond. And initially in the susceptible enzyme, that is AMPC, this methoxy group has to move past a portion of the protein called N152. So asparagine 152 sits here in the way. And the trouble is that these two come in too close of a contact, and the methoxy group simply can't make it past. It runs into the N152. Now, if we make a mutation to the M152 in the laboratory, now we see that the same drug will bind in a different conformation. That is, that it's moved, and it's able to get past that region of the M152. And you'll see that, of course, there are other changes that go on as that motion takes place. And if we superimpose them, you can get an idea that now this motion is able to take place. There's a second motion that has to take place, which is the blue bond rotation. And here we have this carboxylate group, and these oxygens appear as red sticks in the diagram. So this group here is this one here. And what we're seeing is that this group is going to now move around. Where previously it's interacting here with this N346, it's now going to move down and interact with N343. Now, in the moxolactam structure, this is prevented by this methoxy group, but since cephalothin lacks the methoxy group, it's able now to make both of these rotations and come into this conformation. So next, to complete the movement, cephalothin has to go through one more movement, which is the completion of this blue rotation, and come all the way around to the other side of the binding pocket. And we can see this rotation happening by comparing the cephalothin when the key is stuck in the lock versus when the broken key tries to go back into the lock. So we have what's called the cephalothin product. This is the broken key that comes out of the lock after the lock is turned. And in this one, this carboxylate group has now swung around to the opposite side of the binding pocket. So take a look here, and and now it's here, 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 here. So if we look at them together, you can see that this is quite a large motion. Now, the fact that the product binds in this state suggests that all of the motions from beginning to end have to occur before the key can come out of the lock. Now, how does cefoxidin bind in its enzyme? We can compare it to the cephalothin product. Now, if FOX4 is able to turn the key, so to speak, for cefoxidin, we should see it in a similar conformation as cephalothin in AmpC. And in fact, that's exactly what we see. So now, the cefoxidin is able to be turned into this conformation, that is a product-like conformation, which suggests that the enzyme is now able to turn, rather than have the key get stuck into it. And what we notice is that there are some changes in FOX4 compared to AmpC that might be responsible for this. Right? Here down at position 153, you have a proline instead of a serine. Here at the top, you have groups that can interact versus groups that cannot interact with the FOX4. And so we think that these groups may be important, and we're going to be looking into that in the future. So a second area that our lab looks at is the possibility of a different strategy for using antibiotics, and that's to do with what I call the 1-2 punch. So rather than using the one molecule that attacks both of these enzymes, we can instead use one molecule that attacks the beta-lactamase and a second molecule that attacks the cell wall building enzyme. And the great thing about this strategy is we only have to make one new drug. Because if we can block the activity of the beta-lactamase, now our drugs can get through this offensive line, so to speak, and get to the cell wall building enzyme, which is still susceptible to these drugs. So we can use some of the older drugs now and sort of resurrect them for this purpose if we can knock out the yellow packman. And some of these have the names clavulanic acid, tazobactam, and avibactam. Some of you in this room have probably already taken this 1-2 punch combination. Anybody ever taken Augmentin? Some of you have. There's a lot of hands going up. Right? What Augmentin is two drugs. It's clavulanic acid to block the beta-lactamase, and it's amoxicillin to attack the cell wall building protein. So this is a popular strategy right now. One of the latest combinations to come out is avibactam and ceftazidime. Ceftazidime is one of those third-generation cephalosporins. Although resistance is increasing against them, the resistance is due to the beta-lactamase, not to the cell wall building protein. Now, notice that all of these have a similar structure. They still contain this beta-lactam structure. What would also be interesting would be to find some inhibitors that didn't have a beta-lactam structure. Because many beta-lactamases exist, and maybe they know how to get rid of these antibiotics, or excuse me, all these inhibitors already. It turns out that among beta-lactamases, there are 4 different classes. One of them is susceptible to these drugs. 3 of them are not. And so we need some additional inhibitors. And some of them come in the forms of phosphinates and boronic acids. I've been working with boronic acids, and they have this structure. And you'll notice some similarities between the side chains on these boronic acids and some of the drugs that we've looked at tonight. And one thing that we've done is we've been lucky enough to get crystal structures of our enzyme FOX4 in with one of these inhibitors bound inside of it. And so what we do is we can make a comparison between, say, AmpC, the green protein, and it bound to its bound to this drug, and our protein FOX4 bound to the same drug. And what we can look at is how does the same drug bind differently? That is, how does one key fit into 2 different blocks differently? And by doing this, hopefully we can learn something about how the enzyme is functioning and maybe design a drug that will work even better. Although it turns out that these molecules actually do work as drugs. You can give them to mice and the mice get better. So, for the difference between AmpC and FOX4, you'll notice I've drawn in some lines to indicate interactions. So these are the particular molecular interactions that are causing the key to stick in the lock. And what you notice for this white molecule attached to the green enzyme, there are a lot more of these lines than there are for the blue molecule attached to the yellow enzyme. Right? There's only this one. And what we observe is that this green susceptible enzyme binds to the drugs 30 times tighter. So something clearly is going on in this region that is important for the drug to bind. So what do we do? Well, this is our hypothesis. So we'll take the susceptible enzyme, that is the green one, and we'll make mutations to make it look like the resistant enzyme and see if the key fits worse. Or conversely, we can take the resistant enzyme and mutate it so it looks more like the susceptible enzyme to see if we can get the key to fit better. And by taking these two different directions, hopefully at some point we'll meet in the middle and have a better understanding of how the drug and the enzyme interact. And this is precisely what we're doing in our Biochemistry 173 experimental biochemistry course here at Hofstra that's taken by all of our biochemistry majors. And we started this project back in the spring of 2015, and students were making mutations at some of these positions and looking at how we can take a susceptible enzyme and make it resistant. Now this sounds like the wrong idea, right? We shouldn't be making more resistance, right? We're going to have to do that to try to understand how the resistance develops so we can try to get ahead of this problem. And we'll be continuing this research with the class in the spring of 2017. So to summarize what we found, our collaborative team found the first view of the FOX4 enzyme. This is one of these cefoxidin-resistant enzymes bound to cefoxidin. So this was a great discovery that is going to really help our understanding of how these enzymes work. Our structure predicts a possible resistance mechanism that we can now test. And we've also got a new key stuck into the lock that is one of these transition state inhibitors bound into the FOX4 structure. So we're looking forward to developing some of this research in the coming months. So what's next for the group? Test these ideas by making targeted changes or mutations to the FOX4 to see if our hypothesis is correct. We can compare FOX4 to other FOX enzymes. So FOX4 is only the fourth one out of 10. And in this family of enzymes, they're all very similar. There's a small number of mutations separating them, but they all have slightly different activities. FOX4 seems to be the best among them, and we'd like to understand why. And finally, we only seem to have these static pictures, that is, sort of snapshots of the protein interacting with the drug. And what we'd really like to get is sort of a picture of the key turning, more like instead of a photograph, more like a video. And so we're hoping to use fluorescence and Raman spectroscopy to get a time-resolved picture of the key turning in the lock. And hopefully this will give us even more information to use to design new drugs. So we're going to end where we began. Who is going to have the last word? Well, here's the news. No new classes of antibiotics have been developed since the 1980s, which is to say, no new targets have been identified successfully and developed into drugs. So there's a great need to discover new classes of antibiotics so that we have some alternatives to the current targets. However, drug companies who are perhaps the best poised to make these discoveries are not set up to do this kind of work because they can make the discovery, but fiscally it doesn't work out because if they pay $1 billion to develop a new drug, and their doctors say, I'm not going to prescribe that drug, only in the worst possible cases, it's going to take them too long to make back money on their investment. And so in the past few months, drug companies have come as a group to the governments of the world and asked them to pay for antibiotics to be developed. And I think that they're right to do this because this is really a problem that affects everybody. It appears that combination therapy is going to be the way to go. Going forward, 2 drugs are certainly better than 1. And we're going to have to look to alternative modalities for solving the antibiotic resistance problem. It's not going to be simply that we're going to take pills and feel better. We're going to have to develop new strategies, including viruses that infect bacteria, greater use of vaccines, and also antibody therapy. And finally, since all of this is going to take a tremendous amount of time to develop and get right, in the meantime, we need to speed diagnosis of bacterial infections so that doctors are able to prescribe the correct drugs and improve surveillance so that we have a better idea of where resistance is developing and pay attention and direct resources to that area. And finally, everyone needs to do their part. You can support government-funded science by electing leaders that think that science is a priority and make sure that the NIH has increased funding for this research. When you get antibiotics, take the full course. Take Fleming's warning seriously, and don't allow yourself to be the ignorant person who doesn't take all of their antibiotics. Make sure that you kill off all of the bacteria before you stop. Never give away your antibiotics. Right? Unless you're a doctor, in which case you're going to be prescribing them, I think none of you are doctors. So don't save your antibiotics for a rainy day. Don't save them for another time when you're going to get sick so you don't have to go to the doctor, right? I know some of you are nodding your heads. Don't do that anymore, right? You're only contributing to the problem. And don't demand antibiotics from your doctor. We have gotten into this idea through the 20th century that you go to your doctor, you receive a pill, and you feel better. When you're sick, your doctor can tell if it's a bacteria or a virus. If you have a viral infection, antibiotics are not going to help. And they could potentially cause resistance to develop. And finally, wash your hands, right? Antiseptics, good hygiene is the best way to prevent the transmission of resistant bacteria. And also remember, who's using the most antibiotics of all? It's not us, it's our animals. So support farming that reduces or eliminates antibiotic use. This is really key. Many of the resistant infections that we now see in hospitals had their origin on farms, where animals developed the infection, it was spread to the farmer's family and friends, and eventually ended up in a hospital. So if we can only give antibiotics to truly sick animals, we can certainly slow the pace at which resistance develops. Now, we may not be able to stop resistance from developing, but if we can keep ahead of it by continuing to develop more drugs and slowing the pace of resistance, I think that we can prevent some of the dire predictions that are being made today. So, I started today talking about superbugs, and perhaps you're wondering now, where are the superdrugs? Well, the message I'd like to leave you with tonight, you are the superdrug. So I'd like to thank our collaborators on the scientific portion of this work, funding from Hofstra University Faculty Research and Development grants. These are grants given to faculty members on an annual basis to support research activities. The NIH and New York Structural Genomics Center funded our collaborators. We have wonderful undergraduate students here at Hofstra, Dina Bijou and Matthew Noel, the two of them that appear on the publication that describes this work. Emily Wendorf is a wonderful faculty colleague who also appears on this work and helped us with some of the molecular modeling. We have collaborators at Case Western Reserve University and the Cleveland VA Hospital, chief among them Robert Bonomo, who is really a giant in this field, and his research scientist Christina Papp-Wallace, who has been an indispensable help as his research associate. At Albert Einstein College of Medicine, where the structures were determined in Steve Alamos' group, Vladimir Milošević, Rafael Toro worked on the crystal structures. Eddie Neves and Jenny Aguilan worked on another part of the work I didn't talk about tonight. From Liège, we have Jean-Marie Frère, who was really one of the titans of beta-lactamase research, who also advised on this project. From University of Modena in Italy, Fabio Prati and Emilia Caselli, who built the boronic acid molecules. And from La Coruña Hospital in Spain, Herman Blue, who was part of the team that discovered FOX4 and has been developing this work. So thank you very much for your time and for your attention during this long talk, and I'd be happy to take any questions.
All right, thank you for that great lecture. We do have time for questions, so please do come down for questions, and if you have them, and while people are coming down to the microphone, I just want to make sure to thank the Hofstra Cultural Center for helping put on tonight's event. And make sure you stop at their table out front. They have a schedule of upcoming events. So, questions?
Hi, good evening. I have two questions, not chemical questions.
Okay.
You can rest assured of that. But in the last part of your talk, you were discussing how drug companies want governments to sort of put money into this research. I'm curious to know, I know that right now many drugs are developed by colleges and universities throughout the country, yet and still consumers are walloped with these enormous bills from drug companies that use the research that people did to generate. What can be done to ameliorate that situation? That's number one. And the next question I have is, in other countries, distribution of antibiotics doesn't count. So how, if this is a worldwide problem, as you suggested, how is the problem of drug resistance going to be ameliorated if each country has different rules as to how antibiotics are distributed?
Thank you very much. Those are wonderful questions. And let me answer the second question first, or try to address it. So it is true that in this country we do keep very tight control over who can get antibiotics. They must be prescribed by a doctor. And this is for very good reason, because resistance can easily develop if antibiotics are misused. So in order for other countries where antibiotics are not as tightly regulated, we need to have cooperation among governments that will change those practices, right? I mean, part of the problem is a public health problem, which is having consumers understand how to properly use the antibiotics and making sure that they do and take responsibility. The other portion is making sure that governments are taking care of the antibiotics to the extent that they can. And I think having them available over the counter is probably not a very good idea. So that's something that's going to have to be worked out amongst governments, and hopefully through the World Health Organization and the United Nations, maybe some agreements can be reached. As to the problem of the high cost of pharmaceuticals, well, I'm a protein scientist. I don't have a great understanding of how the pricing of antibiotics is made. But what I do know is that for drugs that are invented at universities, they can sometimes be licensed out to private companies. Sometimes small biotech companies will develop a drug or a technique, and then maybe that will become part of a larger pharmaceutical company at some point. Of course, the cost of drugs is too high. Perhaps changes in our healthcare system will be able to bring down the price of drugs through regulation. The particular problem with antibiotics in solving this problem is that antibiotics are not money-making drugs, right? Because not everybody is using them. It's not as though half of the people over age 55 take antibiotics on a daily basis, like they do for certain other kinds of drugs, for example, cholesterol-lowering drugs. Right? Those are drugs that are used by many, many people. And for antibiotics, we really want them to be used sort of as little as possible so that we can preserve the utility over time. And so this, the contribution, I think, of governments and of individuals to solving this problem is really something we all have a horse in this race. Right? We all want to make sure that we can stay healthy for as long as possible. So the cooperation of governments, I think, is going to be essential in seeing that the drug development continues apace. And we've certainly gotten behind in the last few decades.
Thank you. I was going to ask about international, certain countries where drugs are available over the counter, such as India, and that's where the certain resistant organisms come from. And by the way, I'm a registered nurse and work in hospital infection control. So I'll raise a different question just for your comment, and that is, even in the United States, where we do regulate medications with prescriptions and so forth, and have only certain people allowed to dispense them, there's still a substantial lack of understanding, in often cases with physicians, about how to use antibiotics appropriately. And I know that a lot of hospitals have antibiotic stewardship programs in place now to help fine-tune their antibiotic use. Do you have any comment about that at all?
Absolutely. So the example I gave is Toxidin being the highest selling hospital drug in 1984, right? Shows sort of the way that antibiotics used to be treated was a little bit more carefree. And one of the problems that a physician faces in prescribing an antibiotic is that now it's difficult to know when a patient presents with an infection which antibiotic to choose. Right? Certainly you choose a broad-spectrum antibiotic that's likely to kill a wide variety of types of bacteria, but you don't know which it's resistant to immediately. In order to know that, you need to send a swab of the bacterium out to a testing lab, and it's going to take 24 to 48 hours for that the resistances to be known, and then transmitted back to the doctor so that they can make a decision about what antibiotic is most appropriate to give. I mean, how many of you have been to the doctor, received one antibiotic, and had to come back a couple days later to give a second one? Anyone? I see a few nodding heads. Right, so this is becoming a more and more common problem. What is really needed is a way to diagnose the bacteria in the doctor's office, to know what it's resistant to, so that you give the patient the correct drug the first time, rather than a couple of days later, after the infection has progressed and gotten worse. And so there's been a tremendous amount of focus on this in the research community to have for example, a PCR-based test to identify which resistances the bacterium has, in a way that's much faster than the traditional method, which is put it onto an agar plate that contains that antibiotic and see whether it grows or not, right, which takes a much longer time. So diagnosis, I think, is going to be the way to overcome the problem of mishandling of antibiotics.
So basically, we're in an evolutionary arms race with the bacteria.
Yes.
And my question is there any conceivable way that we will ever permanently gain the upper hand? Because no matter what we come up with in terms of new drugs, eventually the bacteria will evolve the ability to go out with them. So is there any, can you, sort of looking into the future, is there any way that we might be able to defeat the evolution that's going on in these days?
Well, unfortunately, I think the answer is no. Right? The nature of biology is that it finds a way. So the important thing for us is to keep drugs in the pipeline, or keep methods in the pipeline that are going to be able to overcome every twist and turn that the bacteria makes. Right? This is an ongoing process. And if we want to keep our way of life without having to change our behaviors radically, it's going to require us to keep up. We're never going to be able to stop the bacteria from mutating. They're everywhere, and they outnumber us greatly. So it's really incumbent upon us and incumbent upon our scientists and our governments to stay ahead of the problem. Right? We're only in this predicament because drug development of antibiotics stopped in the 1980s. We thought that we had enough. And we turned our attention and our dollars to solving other kinds of problems, cancer, diabetes, heart disease, and so on. And while we've made wonderful advances in improving life in those areas, antibiotics have been largely neglected. And it's that neglect that has led us to the superbug problem that we now find ourselves in.
Thank you. One last question.
Okay. To answer most of the questions I had, but the other thought I had was, is there any possibility of an allosteric reaction with the data properties?
So you're asking a question about allosteria, which is when you have a drug molecule that doesn't bind in the mouth of the Pac-Man, but sort of binds on the backside and interacts with it in a different sort of way, where maybe the resistance will be developed at a slower rate.
So how do you do that when disrupting the active site?
Disrupting the active site in a different way. So allosteric inhibitors are really useful inhibitors because when you have a competitive inhibitor, that is something that binds into the mouth of the Pac-Man, usually it's preventing something else from binding there. Right? And so if you get enough of that other compound, you can kind of wash out the inhibitor. And an allosteric inhibitor is more effective because you can't have that sort of competition going on. In the case of the beta-lactamases, I look at the structure of it. There's not a lot of other surface area where you could imagine a drug binding to it. And so it doesn't present the same kinds of options as you have with other kinds of enzymes, where maybe there are those extra pockets on the surface where you might fit a drug into it. Right? Because after all, drug binding is, to a large degree, a surface area problem. If you have a cavity in which the drug can bind, you get a lot more of those different interactions with the different atoms that make it possible for you to have something that sticks well. But if you simply put a key next to a lock as opposed to inside of it, it's really difficult to get it to stick. So unfortunately, I don't think allosteria is going to be a potential mechanism for an inhibitor.
Just let me say, thank you for the quote about the human person.
Okay, great. Well,
Well, I want to thank everyone on behalf of Hofstra University for coming tonight. Please join me in thanking Scott for a great presentation.